Welcome to the 11th lecture of combinatorics. So, in the last class we were discussing about the number of permutations of a multiset of cardinality n, and so we say write like this. When we say multiset, we count the cardinality of the multiset is counting all the repetition numbers, and then the repetition numbers of each type. The first type repeats n1 times, the second repeats n2 times. Say there are k types nk, and this is equal to n1 plus n2 plus up to nk. This is the multiset, and this is the total number of permutations possible is n factorial by n1 factorial into n2 factorial into n3 factorial into nk factorial is what we showed by several examples. Now, this coefficient has also got another name. It is called the multinomial coefficient, this ratio. How does this number this name come? Because we can see that suppose there are k in this k types, k equal to 2, suppose there are only 2 type of things, right. Then there are out of n things we have to put into 2 types, type 1 and type 2, remaining should go into type 2, right. So, type 1 we have n1, and the type 2 we have n minus n1, right. Then the number of ways of permuting this multiset. This multiset contains only 2 type of things. The first type of thing repeats n1 times in the multiset, and the other type of thing, the second type of thing, repeats n minus n1 times. The number of possible permutations is n factorial by n1 factorial into n minus n1 factorial in this case, right. So, here you can see that this is same as n choose n1, right. This is the binomial coefficient n in the expansion of x plus y raised to n. This is the n plus 1th binomial coefficient. So, n plus 1th term will be n choose n raised to n, x raised to n1, y raised to n minus n1, right. So, this coefficient only is coming there, right. So, because this is binomial coefficient, the term this which generalizes this. So, this is when n choose n1 comma n minus n1 is when k is equal to 2, the n distinct objects are a multiset of cardinality n with n1 things of first type, n minus n1 things of second type is permuted. How many ways you can do, this is what. So, but this is essentially a selection of n1 things out of n1. So, in the case of binomial coefficient, you can also see that, for instance, you have if we had considered, we had explained it. So, the distributing n1 things into the box would, when you also give the order to the boxes. In the last class we explained that. That is why this is corresponding. And now we go back to the other thing. So, namely n choose n1, this is the way it is written. So, we also have a notation for that. Because of that, we will the way we write n1 for, we could have written n1 comma n minus n1 for the binomial coefficients. We generalize it and write it like this. This will be called a multinomial coefficient. Multinomial coefficient. Now the multinomial coefficient figures out in the multinomial theorem. Like binomial theorem, we can have a multinomial theorem. Let's say, let's write like this. Suppose we have x1 plus x2 plus x3 plus xt and whole power n, right? There are, so we can write k here, for instance, k types. So then this will be expanded to several terms. You can see that what kind of terms will come. So this will be something x1, x2, x3, xk, and this will be something like, here there will be some coefficient, some a1 will come, there will be some coefficient here, a2 will come, this will be a3, and this will be ak, and so on. And then here this kind of terms will come with some coefficient, right? Like in the binomial coefficients, we have x raised to something into y raised to something with some coefficient is what is happening here, right? But here in the multinomial coefficient, this kind of term with a particular coefficient will come, right? Now how does it happen? x1 plus x2 plus xk into x1 plus, this is the same way we solved the binomial theorem, x2 plus, binomial formula we proved, right? So xk, and similarly we have n times, we will repeat it, x1 plus x2 plus x3 plus xk, right? Now a particular term, right, for instance x1, right, to raised to a1, so x1 raised to n1, let's say, into x2 raised to n2, x3 raised to n3, and xk raised to nk will be a particular term where sigma ni is equal to n, right? Because if you take xi from one here, one here, one here, and all, so there are out of n this kind of terms, in this kind of terms, we are picking up one from here, one from here, one from here. Out of that, n1 x1s you should get, just the way we argued for the binomial theorem. So that can be so this has to go to n1 things should be selected, right? That can be done in n choose n1 ways, right? And then from remaining n minus n1 things, we have to select n2 things, and from the remaining n minus n1 minus n2 things, we have to select n3 things, and so on, right? This is the same formula we wrote down for the earlier one, and then therefore that will give you the same value. The coefficient of this thing will be that n factorial by n1 factorial into, say, nk factorial, which we will write as like this, n choose, though it's whatever it's called, so it's a multinomial coefficients notation, so we'll write like this, n1 comma n2 comma nk and x1 raised to n1, x2 raised to n2, xk raised to nk. That is what, right? This will be the typical term which we will get, right? You can, or if you wanted to argue, this is objects, different objects. For instance, this first term, we can say the first object number 1, a1, this is object number 2, a2, and this is object number 3, and it's like we are placing these objects into a bin labeled x1. This is, the bins are labeled x1, x2, xk, the k different labeled bins. We are placing them into these labeled bins, but we know that n1 of those things should go into this, n2 of those things should go into it, nk of these things should go into this. This way also we can interpret it, right? I mean, the way we have discussed all these things in the last class, we just saying that okay, this also can be seen using one of those models, balls and beans model or whatever, right? Or otherwise we can directly argue and use this kind of a derivation once again and do it. Or otherwise we can set up a bijection with one of the earlier problems we have seen, and then that would also take us back to the earlier one, right. So, this was the multinomial theorem. Now, we will just take a simple example for practice sake. So, here what is the coefficient of x square into y square into z cube in the expansion of x plus y raised to z, right. Okay, this kind of a question, this is very simple. You know that 7 to here 2 plus 2 plus 3, sorry, I meant 5 here, right, because these things should add up to 7, sorry, 5 plus 4, 2 plus 2 plus 3 is, sorry, yeah, 2 plus 2 plus 3 is indeed 7. Okay, I made a mistake. So, therefore, we are just asking for the coefficient of x square into y square into z cube in the expansion of this. That will be the multinomial coefficient 7 2 2 2, right, 7 2 2 2. This is the way you see 7 2 2 3 will be the coefficient of x square into y square into z square, right. This is what we will get. And a plus 2b minus 3c plus 2d plus 5 raised to 16 in the expansion of this one. So, let us write a plus 2b minus 3c plus 2d plus 5, a plus 2b minus 3c plus 2d plus 5 raised to 16, a plus 2b 16. In the expansion of this, what is the coefficient of a square b cube c square d5? A square, we are interested in the coefficient of a square b cube c square d5, b cube c square d5. So, this problem you can see that here this is not like x plus y plus z whole raised to 16 where you could have directly argued, but here the thing is a comes alone, but b comes with a coefficient already here, c comes with the different coefficients, d comes with the different coefficients, and so on, right. So, a plus b plus. So, now what we do is we convert it to some other variables. Let us make it x, let us make this y, and let us make this stuff z, and let us make this say w, right. Maybe we can w x y z we can write. So, we can write this is w, this is x, this is y, this can be z, yeah, and then one more is there of case. So, that okay, v also we can set, okay, w x y z v, right. This also corresponds to a variable, suppose, right. Now, the point is here if you add up 2 plus 3 plus 2 plus 5, what do you get? You only get 7 plus 10 plus 12 only we get, right. Here 16 is required. So, because the total power is 16, so in the expansion of x plus, sorry, w plus x plus y plus z plus v whole power 16, every term should be of this form, right. W raised to n1, x raised to n2, y raised to n3, and z raised to n4, and v raised to n5. And then when you add up this n1 plus n2 plus n3 plus n4 plus n5, we should get 16, right. But here we are getting what earlier 12, right, 12. So, this has to be 4, this has to be 4. So, we are looking for the coefficient of yeah, as we want 2 3 2 5 2 3 2 5 and 5, then this is total, sorry, 2 3 2 3 2 5 4, okay, this is 4, right, 2 3 2 5 4, right. Now, this we know is this number 16 2 3 2, 5, 4, right. This is 16 factorial divided by 2 factorial into 3 factorial into 2 factorial into 5 factorial into 4 factorial, right. This is what we will get, right. 2 factorial into 3 factorial into 2 factorial into 5 factorial into 4 factorial, right. 5 factorial into 4 factorial will be the number here. But then this will be the coefficient of this number x raised w raised to 2, but w as such we know is a, and that is okay, a square. We are looking for a square, so it will be like that. But x raised to 3 will corresponds to 2b raised to 3, that will contribute another 8 into this, another 8 into this, so another 8 will come, because this 2b raised to 3, so b raised to 3 and then this 2 raised to 3 will become 8 here, right. Another y square, what was y square and z raised to 5 are there. Y square is yeah, y is minus 3 square will be coming from the y square, and this 2 raised to 5 will be coming from this, and then finally we have 5 raised to 4 also, right. So that is what, so there will be a 5 raised to 4 in the end, minus 3 raised to 2, and then yeah, so this 2 raised to 5 also, 2 raised to 5. 2 raised to 5. This you have to multiply with this stuff, and then we will get the coefficient. That's what. I hope I have calculated correctly. So it's nothing big. It's just that for the corresponding powers of x, y, z, and w, we have here because some constants are involved there. Their powers should also be considered as constants, and they will come here. That's what. So then next one is this combinations with repetitions. Now we will take another topic. So let's say this is a different kind of problem. So we have suppose 7 boys go to a shop and they all wants to buy pens. In the shop there are only 4 kinds of pens. There are red pens, there are blue pens, and there are green pens, and then there are black pens in abundance. How many the number of pens they want is actually how many ever pens they want in of a certain type they will get, red, blue, green, and black. If each boy buys 1 pen, how many different purchases are possible from the shop owner's viewpoint of view? This is what it's what say, right. So shop owner's point of view means what the shop owner thinks is, I mean, it doesn't matter to him which boy buys which pen. So what matters to him is the number of pens of the type red, how many are bought, number of pens of the type say black pens, how many are bought, and then how many blue pens are bought and how many green pens are bought. That these are the only things which he wants. So now there are 7 boys there, and then 7 things are bought, right. And then the question is, okay, there is this red pens, and then here we have we have green pens, and then we have black pens, and we have black pens, and we have blue pens, right. And the question is which boy goes to which pen, right, buys which pen. So we can think that the boys are indistinguishable in the sense that whoever buys it doesn't matter, and how many of these 7 boys will buy this many pen, this is all we want. So what we do is, to solve this problem we will set up a bijection as follows. Suppose, see, we will first create, first draw 3 bars, right, and we will say that this corresponds to red pens on before this thing, whatever I write is the red pens, and this is for blue pens, and this is for black pens, and this is for green pens, right. Now, if 2 boys purchase red pen, we will put the 2 boys here. If some 3 boys purchase blue pen, then we will put them here, and then so that means total 5, and then remaining, say 1 boy purchases this and 1 boy purchases, we just put them like this. We just separate. I mean, this first part correspond to the red pens purchased, and this corresponds to the blue pens purchased, and this corresponds to the black pens. This can be the one configuration. It can be like right, 4 pens are purchased of the red type, but then no blue pen is purchased, no black pen is purchased, and 3 pens are purchased on the this is another arrangement, right. And then similarly, any, for instance, for any purchase can be put like this, right, and here there will be a certain number of things, and here these bars corresponds to the regions, right. For instance, the blue pens, any blue pen purchase should be put here, and then any black pen purchase should be put here as a dot, and so on, right. So, also if you draw a diagram of this sort where there are 7 dots and 3 bars, right, that will correspond to a purchasing pattern. Why? Because you can just see this region and count the number of dots in that region, that is the number of pens purchased in the red category, and you look at this region and how many number of dots have appeared here. This is the number of pens purchased in the second blue type, and this is the number of pens purchased in the black type, and this is the number of pens purchased in the green type, right. And then this is the way we can map. I mean, this is a bijection we are setting up with a different kind of problem. Here the problem is what? The problem is this. Here the problem is just that we are trying to arrange 3 bars and 7 dots in a line, right, 7 dots in a line. So, there are, in this case the problem is that there are 2 types of things we have to worry about it. One is this bars, right, one type is this, there are 3 of them, and then the other type of thing is 7 dots, right. Here I have wrote dot, yeah, one more. So, yeah, 7 dots we have to. So, now we know that the 7 dots and 3 bars can be arranged in 7 plus 3 factorial divided by 7 factorial into 3 factorial ways. This is the multinomial coefficient 10, 7, 3 which we have studied, right. So, that all those arrangements. The point here is, it is an arrangement, order matters here, in what way we put it, just that these are indistinguishable from each other, and these things are indistinguishable from each other, but the relative order matters other than that, right. Then right. So, this is the way things happen, right. And then on the other hand, the other problem was just that how many ways we can distribute it, I mean, to 4 different categories. So, there it was, we are not really bothered about the order or anything, it is just that combinations, right. We are actually considering multiset of pens, right. We want to create using we have to select 7 things, right, not a multiset. In fact, we are saying that we have to select 7 things, but then there are only, so we can say that only 4 things are available: red thing, blue thing, black thing, and green thing. And then, but then the only thing is they can be repeated here. The green thing can be repeated any number of times, blue thing can be repeated any number of times, black thing can be repeated any number of times, and so on, right. So, this is what we are doing here. So, therefore, mapping into this thing we got the number correctly. This is the multinomial coefficient 10, 7, 3, and this we can easily generalize. Suppose where there were n boys, right, and the pens were like of k types, sorry R. So, let us say we can use R, and this is R boys, and they were the pens were of n types, right. Instead of 4 type of pens, we have n type of pens here. So, the first type 1, type 2, type 3, and type n, and then this n type of pens are there, right. But any number you can select any number of times. For instance, a type I pen can be taken any number of times if you wish. Just that we have to finally make R pens, take R pens out of it. In how many ways you can make it. Again, the question can be mapped to the same kind of thing where we want for the n pens to create n regions for pens, we can use n minus 1 bars, because if you put n minus 1 bars here, region 1, region 2, region 3, so this will be region n. So, n minus 1 bars will create n regions, right. And now in these regions we place the balls in whatever way we want. I mean, how many balls, n r balls should be placed in whatever way. That will, for instance, in any way of placing, it will correspond to one linear ordering of r balls and n minus 1 bars, sorry, r dots and n minus 1 bars, right. So, which means that the total number of ways we can do this thing is n plus r minus 1 factorial divided by n factorial into r factorial, r minus 1 factorial. This is this is because r factorial into n minus 1 factorial. You see, we have n minus 1 bars and r dots, right. So, this is essentially that multinomial coefficient n plus r minus 1 r comma n minus r, right. This is the thing. This is, so therefore, we can generalize it to this formula. I mean, when there are we can tell that there are, when there are n boys, so it's something like this. We have to select n r pens from n type of pens, right. Or maybe there are n things, and then each thing can be taken many times. That is what we are saying. N type of things means, right. So, when we have to make an r selection of size r, then we can do it in n plus r minus 1 choose. So, yeah, this is essentially, because it is not a multinomial coefficient, this is just a binomial coefficient also, because this can be written as n plus r minus 1 choose r, right. Yeah, that is what. So, as we have discussed just before, this r, when we see it as a multinomial coefficient, this is n plus r minus 1, n minus r, n minus 1, because this add up to this, but we all know that this is binomial coefficient only, plus n plus r minus 1 choose r, right. Or it can be written as n plus r minus 1 choose n minus 1, that is also fine. This is also equally fine, right. And then the next one is the next one is another example. So, let us say a sweet shop offers 20 different kinds of sweets. Assuming that there are at least a dozen of each kind when we enter the shop, in how many ways we can select a dozen sweets, right. See, the thing is, there are sweets different variety of sweets, 20 different variety of sweets. The same kind of, so here we have instead of buying pens, we are buying sweets, right, but we have to buy dozen, that means 12 sweets we have to buy. See, when I say 12 sweets, not 12 different type of sweets, we can buy the same sweet more than once, right. We can buy 3 ladoos, 5 jalebis and things like that, right. So, and total 12 we have to make. But then there are 20 different varieties. The only thing is we are worried is, is it possible that I can buy all of them the same time. So, is it possible for me to buy 12 ladoos? We are saying that yes, it is true. So, because for each of this kind we have at least 12 there. So, we do not have to assume that there are infinite number of things available like we were telling in the last thing. Yes, so as long as we are only going to select R things, total R things, as long as each type has R copies, that is more than enough for us, right. So, otherwise we are in a trouble, because some combinations we cannot make, some selections we cannot make. For instance, when we want to buy a dozen things and if we try to take all ladoos, then it may so happen that there are only 11 ladoos and then we cannot make 12 ladoos, right. So, that will decrease from the count, that is what it is. So, then different. So, then how will you solve this question? It's a almost same thing that we did in the last stuff. Here instead of 7 pens we have 20 sweets we have to select. So, that R here is equal to 20, and then the types, that is n is equal to sorry, we have to select 12 sweets, a dozen sweets, and the types is 20, n equal to 20. So, therefore, we know that number of selections we can make is R plus n minus 1 choose R, that is 12 plus 20 minus 1 choose 12. This is what we can make, right. That is 31 choose 12. 31 choose 12. So, 10 rupees should be distributed among 4 boys, A, B, C and D. This is another question. In how many ways can we do this thing? This is the same question. We have 10 things. See, asked in a different way. So, earlier we were buying sweets, we are taking things from here. Here we are distributing things back, in the sense that we can think that we are when we give 5 rupees to boy A, that means we are selecting the boy A 5 times, right. To give first rupee, 1 rupee is given to A, that means boy is selected once, second rupee is given, the boy is selected a second time, and then the third rupee is given, he is selected a third time, and so on. So, therefore, the question is same, just that we want to select this boys 10 times, each boy we can repeat the boy, right. Say for instance, a particular boy can be repeated several times, that is the only difference. So, therefore, here what do we see? So, the question is very simple. Instead of pens we have boys here. How many type of pens? This is the number of boys, that is n equal to 4, right. And how many pens are to be bought? That means 7 in the initial problem, or dozen 12 in the second problem. That corresponds to 10 rupees here, right. R equal to 10 here. So, in how many ways you can distribute it? That is 10 plus 4 minus 1 choose 10, right. This is the total possible ways. That is okay. This is the formula, R plus n minus 1 choose R. This is the possible ways, right. Okay. So, now this is a question we have already seen several times. Now, we are asking a slightly different question. Suppose if each boy has to get at least 1 rupee. For instance, suppose see, we called 4 boys and then we do not give anything to some of them, that is not good. So, we decide that at least 1 rupee should be given to anyone, then you can do anything you like. Then how will you do it? So, the trick is just that. So, it is very easy to do this thing. First distribute, we have 10 rupees with us, then first distribute 1 rupee to each boy, that means 4 rupees are gone, right. Now, only 6 rupees are left. The question is, you can distribute this 6 rupees to 4 boys. Now, we can also we have the provision not to give any rupee any money to any some boys, right. It's okay. So, therefore, here then 6 and 4 are the numbers. 4 number of types we have is 4, that means n equal to 4. It is like we have 4 objects, each object is allowed to repeat, 4 type of objects, and each object of a certain type is allowed to repeat, and then we have to take it 6 times. You know, though rupees are given to the boys, it is like we can think that 6 boys are selected. For each rupee a boy is selected to be that rupee to be given, that is what. So, then the answer is again r plus n minus 1, choose r. This is 6 plus 4 minus 1 is 3, choose 6, right, 9 choose 6. This is the answer for this, right. And then next question we want to consider is a similar one, but a little more sophistication added here. If A has to get at least 5 rupees and each has to get at least 1 rupee, if A has to get at least 5 rupee and each has to get at least 1 rupee, then what? So, then the same idea can be used. So, A has to be given 5 rupees, so give it to him. So, out of 10 you already finished 5 rupees, now we have only 5 rupees left. Now, each has to get 1 rupee. A already got 5 rupees, then we do not have to worry about them. There are 3 more boys, B, C and D. So, they should get 1 rupee each. So, give them the 3 rupees is used for that, then we have 2 rupees left. Now, the question is, how do you distribute this 2 rupees among 4 children, where we are allowed not to give any money to some boys, right, some boys. So, A, B, C, D, it is clear that we have to do that now, because it's only 2 rupees and 4 boys, some 2 of them at least will not get anything, right. So, but this can be done in how many ways? So, because here the number of types is again n equal to 4, r equal to 2. So, we have 2 plus 4 minus 1, choose 2 ways of doing this thing, that is 5 choose 2 ways of doing this, right. 5 choose 2 ways of doing this, right. So, right. Now, the next one, so we this problem has some idea here, in the sense that we are, we can rephrase the, see the question, like in the earlier one we can say like this. Suppose we have to select n things out of n type of things, right, with repetition, in the sense that we are allowed to that a certain type we can repeat any number of times, we are not restricted that we can take it again and again, but we have to make r of them, right. And then but we put the extra condition that at least one should be given to each, sorry, it would be taken of each type, at least one should be taken of each type. Then what will happen? There are total r things to be selected, right, n types are there. Then, you know, because for each type we have to select one, so we have to already we have to anyway select it. So, we will after that selection we have only r minus n things to be selected, but this r minus n things can be selected in such a way that we can avoid some type also, we can take or not take, right, it does not matter, even 0 number of things can be taken of a certain type. So, that will be r minus n, instead of r we have r minus n plus, now number of times is n and minus 1, choose r minus 1, r minus n, right. How much is this? So, here n will cancel off, that will just become r minus 1, choose r minus n, sorry. So, yeah, so we can also put it as r minus 1, choose n minus 1 if you want, right, because if you add this thing you will get r minus 1, right. By symmetry rule we can also write it like this. So, this is a nicer formula, because it looks nicer, at least r minus 1, choose n minus 1, right. Here the only condition is that every type has to be taken at least once, that is the only extra condition we put, right. We know the technique is there, we also, so even more complicated conditions can be put, though we do not attempt to get a general formula for all these things, all those things, right. and then now let us see a different formulation of this problem. So, which is also, as I was telling, in combinatorics it is very common to talk of balls and bins problems, and so many. So, here this is a formulation in terms of balls and bins. We have R identical balls and n distinct labeled boxes. In how many ways we can distribute these R identical boxes among n distinct labeled boxes, right. So, these R identical boxes now corresponds to a selection of R, that is what, and n distinct label boxes correspond to the types, that is what we want to tell. So, we will show that this is the same problem, because when we wanted to select R things from n different types, what we did is we drew n minus 1 bars, so that we created total n regions here, and these are selections depending on how many selections are taken from this type, this type, this type, this type and this type. We decided to put so many dots here, right. Now, when we put these dots, we can also think of, so many dots are put. So, like we can think that, for instance, we can create, say this is a box and this is another box, this is another box, we can imagine like this is another box, this is another box, right. So, from each region can be considered as a box, and these are labeled boxes, because this is the first box, this is the second box, this is the third box, this is the fourth box, and this is the fifth box and so on, right. Now, we want to put this R identical, because here it does not matter, because they are just dots in we just have R dots, that R dots should be placed in some way. It is just R identical balls being placed in these boxes, that is what it says, right. It does not, it is only the relative numbers which goes to the boxes that. So, you can clearly see that there is a bijection between this and this problem, the earlier problem. Therefore, naturally this question of placing R identical box into n different boxes, distinct boxes. Distinct boxes means the boxes are labeled, they can be distinguished from each other. It can be modeled using this R identical boxes and then distinct boxes. We can model it using this this bar and dot thing, and that same the earlier problem also was modeled like this. Actually, both have a bijection to this. So, therefore, both problems are same. The sense that, so this here, as I pointed out, these are identical balls, the number of identical balls corresponds to the size of the selection we want to make, how many things we want to select, and the boxes correspond to the types, each box corresponds to a certain type, and R balls are placed into boxes, R balls are placed into boxes, right. That is the correspondence, because it is like when we are taking a certain type, it is as good as placing that ball into that box, right. That is the way we are mapping those two concepts. So, therefore, this number is also R plus n minus 1 choose R, like the same number as before. And the earlier problem will correspond to like this, when we say that a particular type of object should be taken at least once, each type of object should be taken at least once. Here we are saying that each box should contain at least one thing, there should not be any non-empty box is the corresponding formulation. Then the number will be, as we have seen, R minus 1 choose n minus 1. So, also we can remember, right. So, this is the balls and bins way of talking about the same problem. The problem is same, just that we when we see something like this also we have to identify it. At one look it may look different, the two problems may look different, but if you think for some time you will realize that both are one and the same. So, it is good to remember all the variations of the different ways in which it is formulated, right. The same problem is asked, right. Sometimes it will be easier to think in terms of this one, or sometimes it can be easier to think in terms of the other way. So, now the next question, in how many ways can we distribute 7 bananas and 6 oranges among 4 children, so that each child receives at least 1 banana. This is the next question, right. This is at least one banana. So, this is also the same kind of problem, but here we have 7 bananas, right, and 6 oranges, and how many children? 4 children are there, right, 4 children, and but the only condition 4 children are there. The only condition we have placed is that each child should get at least one banana. Right, each child should get at least one banana. Right. Okay. So, we can start with the bananas. So, this question can be attacked like this. First, we will see how many ways we can distribute the bananas. Then we will see in how many ways we can distribute the oranges, and then multiply the total number of ways to distribute the bananas with the total number of ways to distribute the oranges. This will give you the total number of ways to distribute 7 bananas and 6 oranges. Just application of multiplication principle. But first question, 7 bananas should be given to 4 children, right. Now, see, each child can now be thought of a container or box, like the child 1, right, child 2. So, I am using the just previous problem to map this one too. So, each child, this is 4 children, and then 7 bananas, but only thing is we have to make sure that all of them get at least one. So, that means one should go here, one should go here, one should go here, one should go here. So, 7 minus 4, 3 only is left. Now, 3 should be distributed to 4 children. Now, we know 3 equal to R, right, because R identical balls, because bananas are identical here. The bananas corresponds to the identical balls, and the children correspond to the beans, right. So, 3 plus 4 minus 1 choose 3. That means 6 choose 3 ways. So, we could have directly used the previous formula, R minus 1 choose n minus 1 also, where R was the 7 bananas, n correspond to 4 children, and we are looking at a situation of these 7 identical balls correspond to the bananas, and then children correspond to the boxes, 4 boxes, so that no box is empty, at least one child, one banana is given to each child. That would have, here we would substitute 7, we would substitute 4 here, that would have given us 6 choose 3 anyway, right, if you wanted to use the formula directly, right, the formula we derived in the last problem. So, this is 6 choose 3, if you remember it. Then the other problem is 6 oranges should be distributed to the 4 children, right, 6 oranges should be distributed, 6 oranges. Now, this is easier because there is no extra condition. So, 4 children should be considered 4 boxes now, right, and then the 6 oranges are the 6 identical balls, right. Now, 6 identical balls have to be distributed to 4 boxes, and that is 6 is R. So, 4 minus 1 choose 6, that is 9 choose 6. This is the number of ways to do this thing. So, that is 6 choose 3 into 9 choose 6. 6 choose 3 into 9 choose 6. Okay, this will be the total number of ways to distribute the bananas and oranges. It's a typical problem, is that we have used all the concepts we have studied, right. And now, the next one. So, here is a little longer problem. A message is made up of 12 different symbols and is to be transmitted through a communication channel. In addition to the 12 symbols, the transmitter will also send a total of 45 blank spaces between the symbols, with at least 3 symbols between each pair of consecutive symbols. In how many ways can the transmitter send a message, right? So, what we are asking is, suppose, see, instead of 12 symbols, let us say 3 symbols A, B, C. This somehow how many messages you can make. So, you may say that you can make A, B, C, A, C, B, these are all possible messages. A, B, B, C, A, B, A, C, and C, A, B, C, B, A. These are the 6 possible ways, 6 ways we can send the, in which we can send the message, right, make the messages, right, for each message. But the complication is that, suppose if A, B, C is a message, the system, the transmitter will add lot of blank spaces, right. So, it is something like the A is sent first, then the transmitter may add some blank spaces, 3-4 of them, and then B is sent, then the transmitter may add a few blank spaces, then again this is sent, like that. So, after the last this thing is sent, nothing. So, the total number of blank spaces sent by the transmitter is 45, and the condition is that at least 3 blank space will be there between any of them. It can be from starting from 3 onwards up to 45, not, because everybody has to get 3. So, like after ensuring 3 in between each of them, you can see how many will be left. That can be added arbitrarily by the transmitter between any pair of letters. So, this is, let us say, A1, A2, A3. So, these are the letters, A12 are the letters. We know that 12 factorial messages can be formed because there are 12 symbols, right. So, for each message, how many gaps are there, how many between the letters, how many gaps are there? See, for instance, this is A1, between A1 and A2 there is a gap, A2 and A3 there is a gap, and between A3 and A4 there is a gap, and between A11 and A12 there is a gap. There are 11 gaps, right, 11 spaces between 2 letters, and then these spaces, each of them will anyway get 3 blank spaces. See, 3 blank spaces will be obtained by each of them, right. So, that means 3 into 11 is equal to 33 spaces will be anyway spaced like that. Now, but we have total 45 blank spaces, that is 45 minus 33 spaces. That means how many? It is 7 plus 5, 12. 12 extra spaces has to find some position, right, and this position has to be, say, between the messages. For instance, this is A1, A2, A3, A4, as you can see till A12, A11, A12. So, as you can see here, this can be considered as boxes, right, the box 1, this is box 2, this is box 3, and this is box 11, right. There are 11 boxes, and each box, in each box we can put either 0 or 1 or up to, even if necessary, all of these 12 spaces, right, because 3 already we have given, and on top of that we are saying that all the 12 can be placed in the same gap, or 1 can be placed, or 0 can be placed, or any number can be placed out of this 12, right. So, we know that this is now labeled boxes, right. There are how many labeled boxes? 11, that will be n, and the number of identical balls correspond to the number of spaces, that is R equal to 12. So, the number of ways we can do is 12 plus 11 minus 1, choose 12, that is 12 plus 10, that is 22, choose 12, right. This is the number of ways we can do that, right. Right. So, if you want to like go back to the original problem of selecting R things from n different type of things, we will have to consider this 12. For this 12 blank spaces, we have to select the gaps, which gap should it correspond to, it should go into, that is the way. either this one or this one or this one or this one or this one should be selected for each blank space to be put, right. So, we have to select these objects, these 11 objects. The repetition is allowed, and for instance a particular object can be repeated many times, but total we have to select 12 of them because there are 12 spaces. That is why that is how we interpret the situation in terms of the first problem, the original problem we considered. That means the selecting r things out of n things where each thing can repeat, right. And now the next one we will consider. Okay, fine, we haven't completed the answer here, because what we have done is, this is the way we can arrange the blank spaces, the number of, but then you remember there were 12 factorial messages. For each messages we can do this distribution of blank spaces among the gaps, that is total of 22 choose 12, 22 choose 12, right. This many ways we can do this thing, 12 factorial into 22 choose 12 ways. Now the next question, so the next we will consider a slightly different way of looking at the same thing, or using a number theoretic question. So, we want to say find the integer solutions to this equation, x1 plus x2 plus x3 plus x4 is equal to 7. But the only thing is each xi has to be at least 0, 0, 1 or 2 or 3 or 4, because we are only going up to 7. So, xi has to be greater than 0, that means it can only go up to 7 for each of them. How many ways, how many solutions are there for this thing, right? This question we will discuss in the next class.